We like to believe that size always means power when it comes to animals. After all, in the wild, you often see the biggest predator, the tallest giraffe, the heaviest elephant, the longest shark. These are the winners. You might assume that in the long story of evolution, bigger often meant better. But what if I told you that in one branch of the tree of life, colossal snakes bigger was a gamble, an experiment that reached astonishing extremes but ultimately led to nowhere? What if the greatest serpents that ever slithered the earth were not triumphs of evolution but dead ends, relics of unrealized potential? To understand this secret history, we must travel back tens of millions of years to equatorial rainforests so hot and humid that modern jungles seem chill by comparison. The continents themselves were in flux, the climate sweltering, ecosystems raw and unbalanced. In this primeval world, limbless giants emerged, snakes that exceeded anything alive today in length, girth, and sheer ecological dominance. These were not your familiar pythons and boas. They were experiments in gigantism, creatures that pushed the limits of reptilian design. Yet despite their size and might, their lineage did not lead to living descendants that rival them. Their story is a reversal of expectation. Immense size was not a doorway to dominance forever, it was a doorway to extinction. Before these giant serpents rose, we must consider the normal story of snakes. Today, snakes range from tiny thread, snakes a few inches long, to reticulated pythons over 20 feet. Most snakes thrive by being stealthy, by adapting to a modest niche, burrowing, climbing, swimming, ambushing. They don't need to weigh a ton or measure 50 feet to succeed. Evolution rewards flexibility more than sheer magnitude. So it may surprise you that in deep past, some snakes abandoned flexibility in favor of one thing: size. The first monster in this hidden saga is the famed Titanoboa cerrejonensis, discovered in the coal-rich Cerrejón Formation of northeastern Colombia. Fossils of dozens of individuals emerged in the early 2000s, finally described in 2009. Researchers estimate this snake stretched around 12.8 meters, about 42 feet, in length, perhaps even up to 14.3 meters, 47 feet, and weighed well over a ton. Wikipedia 1. In a swampy tropical archipelago rising from the Paleocene seas about 58 million years ago, Titanoboa was likely the top predator. Imagine a serpent so large that its body could coil dozens of times to fill a small lake. Its head alone might have been roughly the size of a human torso. Its prey? Large turtles, crocodile relatives, big fish, all of which were abundant in that post-dinosaur world. Fossil evidence suggests its diet included giant lungfish and osteoglossomorph fish, other reptiles, and even crocodilians. AZ animals, too. Its skull morphology, jaw structure, and vertebral robustness all point to a constrictor that could crush and swallow massive prey. Smithsonian Magazine 3. But why did Titanoboa get so big? The answer lies in the climate and environment of the time. Snakes are ectothermic, they rely on external heat to regulate their metabolism. In a world where mean annual temperatures at the equator were perhaps 34 degrees Celsius or more, and stable year-round, the thermal conditions allowed reptiles to grow larger than they can today. Encyclopedia Britannica 4. The flooded rainforests, slow rivers, abundant prey, and low competition in some niches created circumstances where gigantism was viable. In this setting, Titanoboa was not just large, it dominated. It lived in a wetland environment of coal, forming swamps, shallow lakes, and rivers. Its body coiled beneath vegetation, rose to strike fish in shallow water, or crush turtles that sunbasked at river edges. The fossil site reveals a fauna of giant turtles, crocodilians, lungfish, an ecosystem fundamentally shaped by one giant predator. One can almost picture it: a serpent the size of a bus, sliding silently into black water, strike lightning, fast, and vanishing into the green gloom. And yet, even a creature of such magnitude did not survive forever. Its lineage too came to an end, because the world around it changed. The marshes dried, climates shifted, prey composition altered, competition increased. And when the environment that enabled its gigantism collapsed, the massive snake could not adapt. Its size that once assured dominance now made flexibility impossible. But Titanoboa was not alone in the death grip of gigantism. Another lesser-known but equally fascinating giant serpent is Vasuki indicus, recently described, 2024, from the Narration Formation of Western India. Fossils of 27 vertebrae were recovered from lignite mines in Gujarat. Researchers estimate body lengths from about 10.9 meters, 35.8 feet, up to 14.5 meters, nearly 50 feet. Eiffel Science. 5. This snake belonged to the extinct snake family Matsoidae and lived around the Middle Eocene, roughly 47 million years ago. What makes Vasuki compelling is that it may have topped or at least rivaled Titanoboa in length, and yet belonged to a quite different lineage in a far-flung geography. The existence of these two gargantuan snakes, in two separate continents and two separate snake lineages, raises daunting questions. What triggered these giants? How did evolution arrive at such extremes twice? And why did they disappear? To answer these, we look into their adaptations and their flaws. One key adaptation shared by giant snakes is *** body elongation and robustness ***. By extending vertebral count and thickening vertebrae and ribs, these animals increase their length and mass. In Titanoboa, scientists used vertebral dimensions to extrapolate length and weight, comparing with modern large boas and anacondas. The result: estimates up to 14 meters and over 1,000 kilograms. Wikipedia 1. For Vasuki, vertebrae width gave length estimates that rival Titanoboa, even if mass remains uncertain. Wikipedia 6. Another adaptation. *** semi-aquatic life habit ***. The habitats of these giant snakes were typically slow-moving rivers, swamps, coal-forming wetlands. For Titanoboa, evidence suggests it was more aquatic or semi-aquatic. Its size would have made terrestrial movement cumbersome, and its prey largely aquatic or river-edge dwelling. Smithsonian Magazine. 3. In such waters, buoyancy aids a heavy body, and ambush from submerged coil becomes viable. Third adaptation, ***, feeding on large prey, ***. To sustain such body size, the snake needed abundant large prey, giant turtles, crocodilians, big fish, all present in its ecosystem. Titanoboa's anatomy supports a constrictor lifestyle capable of taking down prey much larger than modern snakes handle. Extinct animals. 7. In the case of Vasuki, its environment included crocodilians, turtles, early whales, and fish, suggesting similarly large prey items. Wikipedia 8. 4th. ***, warm stable climate, ***. As noted, ectothermy places upper limits on size in cooler or more variable climates. Evidence from Titanoboa's range suggests equatorial temperatures high enough that giant reptile metabolism could remain optimal. Encyclopedia Britannica. 4. In contrast, once climates cooled, snake-size ceilings lowered. With these adaptations in place, the stage was set for some of the largest serpents ever seen, and for a time, they ruled their world. But then the reversal. The vulnerabilities inherent in gigantism began to show. The same traits that achieved supremacy became liabilities. Consider this. A massive body means high metabolic demand, even for an ectotherm, limited mobility on land, slower reproduction, longer maturation times. When environments are stable, these are survivable trade-offs. But when change accelerates drought, cooling, prey loss, the heavy body becomes a millstone. For Titanoboa, evidence suggests that the coal swamp habitat in Colombia changed. Rivers shifted, swamp forests retreated, prey assemblage altered. The combination of lower global temperatures and perhaps competition or predation may have eroded its niche. Smithsonian Magazine. 3. For Vasuki, isolated in India, a similar pattern may have followed. Changing climate, evolving prey and predator dynamics, and a lineage incapable of shifting to smaller forms. In other words, size that once conferred dominance transformed into fragility. The giant snakes could not downsize quickly, could not adapt to changing prey dynamics or cooler conditions, and their reproduction likely could not keep pace with extinction pressures. Their lineages ended. Modern snakes, by contrast, are more modest in size, more versatile in habitat and diet, and can reproduce faster. Their success lies not in giant bulk, but in adaptability. So the thesis is reversed. The biggest snake did not become the enduring snake. The largest serpents were spectacular but ephemeral. They were evolutionary gambles that failed. But the payoff is profound. The fossil giants tell us about past climates and ecosystems in ways that smaller animals cannot. Titanoboa's size implied mean annual temperatures of at least 34 degrees Celsius in its region, warm enough that today's reptiles cannot match it. Wikipedia, 9. The discovery of Vasuki hints at once. Wider distribution of giant snakes and raises biogeographic questions. How did such enormous snakes emerge in South America and India? Did Gondwana break up, climate corridors, or the spread of swamp habitats facilitate repeated evolution of giant constrictors? Mapping the evolutionary tree of these giant snakes shows that they were not ancestors of today's big snakes, but side branches, lineages that reached extremes and terminal forms. Titanoboa belongs to Boidae, the boa family, but does not lead to modern anacondas. Vasuki belongs to the extinct Matsoidae. Their gigantism appears as convergent evolution, two lineages independently evolving enormous size under favorable conditions. Let us walk again through their rise and fall. In the Paleocene, dinosaurs were gone. The Earth's climate was adjusted accordingly. Warm, greenhouse, equatorial swamps widespread. In the Cerrejón region of Colombia, vast coal-forming wetlands covered the plain. Here, Titanoboa's prey roamed. Giant turtles, crocodilian relatives, large lungfish in sluggish rivers. Titanoboa emerged from a precursor boa lineage and grew into this niche. Its body coiled beneath water or near riverbanks, waiting, then striking with crushing force. It swallowed prey that modern snakes cannot legitimately contemplate. Its length and girth allowed it to dominate, but gradually the climate shifted. Rainforest wetlands receded, temperatures dropped slightly, tectonics and sea levels changed. The massive snake's niche shrank. As competition from other predators or increasing crocodilian size changed the ecosystem, Titanoboa's specialized lifestyle became a risk. Larger predators turned up, prey changed, and the giant snake could not adapt fast. Eventually, its lineage ended. The swamp plains turned to drier habitats, and snakes of moderate size took over. Meanwhile, in India, during the Eocene, the newly described Vasuki emerged. Marshes, backswamps, and wetlands in the Kutch district of Gujarat supported rich fauna, crocodilians, turtles, fish, even early whales. Vasuki, estimated at up to nearly 15 meters, took advantage. Its vertebrae show robustness, suggesting a heavy, long body suited for ambush. It may have been terrestrial or semi-aquatic, differing from Titanoboa's likely fully aquatic ambush style. Wikipedia, 6. Its evolutionary lineage was separate. Again, giant size was reachable when conditions allowed. But again, the inevitable happened. As climates cooled, wetlands receded, competition increased or changed, the lineage died out. Vasuki left no modern descendants. These parallel stories show repeatable patterns. Favorable climate, plus abundant large prey, plus swampy aquatic habitat, equals potential for snake gigantism. But shift any of these variables, cooler climate, dry habitats, prey shift, competition, and gigantism, becomes maladaptive. Another component. As snakes grow larger, their prey options contract. A giant snake cannot maneuver like a smaller one, cannot climb trees or hide in small crevices, cannot prey on small, agile animals efficiently. It is constrained in habitat, prey size, reproduction. Smaller snakes retain versatility. So a giant snake is a specialist par excellence, but specialists are vulnerable to change. What does this teach us about evolution? It teaches humility. It teaches that evolution does not aim at maximum size or endurance of a lineage. It simply works with opportunity and constraint. Gigantic snakes represent an extreme of possibility, not a step toward modern success. They remind us that evolutionary peaks can end in failure as much as success. They remind us that present-day size and survival are not guarantees of future dominance. They remind us that the winners you see today might not be the winners tomorrow. Today, we still marvel at modern large snakes, reticulated pythons over 20 feet, green anacondas up to 17 feet or more, but they pale in comparison to the giants of the past. And they exist in very restricted niches compared to the world-filling dominance implied by giant serpents like Titanoboa or Vasuki. The fossil giants are more than just spectacle. They are data points in the record of life that show how deeply climate, prey, and environment define what is possible in evolution. The story of the world's biggest snakes is also a mirror for our own time. We live in an era of rapid climate change, ecological disruption, habitat shrinkage. The conditions that once allowed gigantism in snakes no longer exist. Wetlands give way, temperatures shift, prey ecosystems change. That helps explain why we no longer have snakes that size. But it also warns us that present ecosystems are ephemeral. What dominates now might disappear if underlying conditions shift. Just as giant snakes vanished when their world changed, so too might large species today face extinction if the world turns. In the end, the greatest snake did not become the enduring snake. The mightiest serpent left no living heirs. The lineages that reached the extremes of size collapsed into extinction. The secret history of these giants is silent but profound. It whispers through vertebrae and coal seams, through tropical swamps now turned to dry land or mined for coal, through islands of fossils and sediment. It tells us that nature's experiments are many and that only some succeed. And so, the next time you see a large snake, admire it, but remember that among its ancestors were beasts of unimaginable scale. Among its cousins were titans that no living creature ever witnessed, giants that ruled their realms and then vanished, leaving only bone and coal and the deep whisper of what might have been. The world of serpents is bigger than you imagine, and its history is stranger still. In this broader story, the world's biggest snakes become more than curiosities. They become symbols. They symbolize the limits of adaptation, the fragility of specialization, the power of environment to create and to destroy. Their fossils hold the keys to ancient climates and ecosystems. They challenge our assumptions about how life evolves and succeeds, and they promise that the spectacular failures of deep time may teach us more than the comfortable successes. We live now on a planet still teeming with snakes, large and small, but none that compare to those giants of old. Yet the echo of their coils still lies buried beneath rainforest soils, in lignite beds, in Indian swamp deposits, reminding us of the secret history of serpents. They were born of heat and swamp, grew to unimaginable length, and then vanished when the world cooled or dried or changed its hydrology. Their story is a testament to the idea that dominance today does not guarantee survival tomorrow. So remember this: the biggest is not always the last. The longest is not always the greatest. And sometimes, the most astonishing creatures are the ones who tried and failed. In the silent fossil record of the giant snakes lies a warning and an invitation. A warning that nature's rules can change, and an invitation to explore the hidden corners of deep time, where the world was wilder, stranger, and far more gigantic than we ever imagined. Because in the end, the secret history of the world's biggest snakes is not a story of triumph. It is a story of ambition, excess, and collapse. It is a reminder that even the most gargantuan of creatures can vanish, and that survival belongs not to the largest, but to the adaptable. The coils of Titanoboa and Vasuki may no longer suffocate giant turtles or slide through swamp rivers, but the lessons they leave behind are still alive. Every time we study them, we peer into a world where limits were pushed and where even a super snake could be brought low. And perhaps most humbling of all, one day our own species may look at the fossil record and see that we too once seemed unstoppable. We too may have reached peaks. We too may face conditions we cannot adapt to. The story of the giant snakes shows us that the wild does not reward permanence. It rewards fit, flexible, responsive life. And so the world's biggest snakes, for all their size and terror, now serve as teachers from a past we can scarcely imagine. Their coils may have unwound into dust. Their swampy kingdoms may have disappeared under shifting climates. But their legacy endures in museums, in journals, in the very idea that life dares to try extremes. Let the secret history of the world's biggest snakes remind us that being big and being lasting are not synonyms, that sometimes the boldest designs in nature are the shortest lived, and that in the branching forest of evolution, the most spectacular branch often ends abruptly. And there, in the fossil record, we find our proof that even beasts of 1,000 pounds, longer than an 8-car train, once slithered the earth and then disappeared. They were not the triumph of life. They were life's wild experiment at maximum scale. And though they're gone, their story remains. Because the greatest snake that ever lived is also the greatest snake that never lived long enough.